To plot phase angle plot, we'll use this table which we have calculated previously. So from this table, if we observe the angles, the limits of angles is minus 93 degrees is the limit, the first limit which we have, and the second limit which we have is minus 236 degrees. So we have to incorporate these values on our semi-log graph sheet. So let me consider minus 240 degrees, the bottom over here, and let me consider 20 degrees gap or 20 degrees difference in one division. Minus 220 degrees, next minus 200 degrees, minus 180 degrees, minus 160 degrees, minus 140 degrees, minus 120, minus 100 degrees, minus 80 degrees. So along y-axis over here again we are considering phase angle. Along x-axis, in previous magnitude plot whatever we had taken omega, that remains as it is. Next what we do is, so depending upon the table, what the values in the table whatever we have got, we'll plot. So for omega is equal to 0.1 radians per second, the value of angle which we have got is minus 93 degrees. So we have to plot that. So when omega is equal to 0.1 radians per second, the angle which we have got is minus 93 degrees. So if we observe, one box here indicates 20 degrees, or one division here indicates 20 degrees. In one big division we have 5 small divisions or 5 small lines. So if one big division indicates 20 degrees, one line here indicates 20 divided by 5, because we have 5 lines here, 1, 2, 3, 4, 5. So 20 divided by 5 will give us 4 degrees. So one line indicates 4 degrees. That means here if we have 80 degrees, next line indicates 84, next 88, 92, 96, 100, 104, 108, 112, 116, 120, 124, 128, 132, 136, minus 140. Like that it will continue. So one division, one small line, one line indicates 4 degrees according to the consideration which we have taken. For the first case, when omega is equal to 0.1 radians per second, the angle which we have to plot here is minus 93 degrees. So this is 80, next line indicates minus 84, minus 88, minus 92, here minus 96. Somewhere in between, after minus 92, we have to consider minus 93. So approximately let me plot at this particular point. That means somewhere over here at 0.1, omega is equal to 0.1, the angle which we get is minus 93, somewhere over here. So this is for the first case. Similarly, for the second case, when omega is equal to 0.5, the angle which we have got is minus 104 degrees. Minus 104 degrees. That means when omega is equal to 0.5, 0.5 means this is 0.1, 0.2, 0.3, 0.4, this is 0.5. So when omega is equal to 0.5, somewhere over here, 0.5, the angle which we get here is minus 104. Minus 104, this is 100. So one division indicates 4 degrees, minus 100, minus 104. Minus 104 will be somewhere over here. So minus 104, we have to plot it over here exactly when it coincides with 0.5 radians per second. So it will be somewhere over here. Similarly, we'll plot all the points according to the table which we have got. So when omega is equal to 2.5 radians per second, the angle which we have got is minus 150 degrees. So 150 degrees will be somewhere over here. So we have plotted a point there. When omega is equal to 3, the angle which we have got is minus 156. Minus 156 will be somewhere over here. Next, when omega is equal to 10 radians per second, the angle which we have got is minus 210 degrees. So we have plotted there. And finally, when omega is equal to 20 radians per second, the angle which we have got is minus 236 degrees. So after this, what we have to do is we have to join all these points. In phase plot, we can either use freehand joining, or if you're uncomfortable with it, you can go with scale. One thing which you have to remember is for magnitude plot never use scale, whereas for phase plot we can, or for magnitude plot always use scale. For phase plot we can use either scale or we can use freehand connectivity. After this we have to find out what is phase crossover frequency. To find phase crossover frequency, we have to consider phase reference. Always minus 180 degrees will be considered as phase reference. So for this minus 180 degrees, draw a horizontal line. Minus 180 degrees, draw a horizontal line like this. Draw a horizontal line for minus 180 degrees, which is the phase reference. Similarly, 0 dB was reference for our magnitude plot. Similarly, for our phase plot, minus 180 degrees is our phase reference. Next, exactly we have to locate the point where the phase reference, this phase reference and the phase plot will be meeting at a point. So that point should be found out. So mark that particular point. If we observe, so minus 180 degrees, this is our phase reference, and this is our phase plot, whatever we have got. Exactly at this particular point, the phase plot is coinciding with our phase reference, and from that particular point, draw a vertical line such that it touches the x-axis. So if you observe, it touches x-axis at this particular point. That particular point or that particular frequency where this phase reference is touching this phase plot is called as phase crossover frequency. Phase crossover frequency, we represent it as omega PC. So if we observe, omega PC is approximately equal to 5.6 radians per second, approximately equal to 5.5 to 5.6 radians per second. Okay, so this is how we plot, or this is how we get phase crossover frequency. If we observe, the gain crossover frequency which we had obtained from magnitude plot was 5 radians per second, and the phase crossover frequency which we have got is 5.6 radians per second. So because the gain crossover frequency is lesser than phase crossover frequency, we can tell that the given system is stable system. Always we have to remember this condition. When gain crossover frequency is lesser than the phase crossover frequency, the system is said to be stable system. So the gain crossover frequency which we have got here is 5 radians per second, and the phase crossover frequency which we have got here is 5.6 radians per second. So because gain crossover frequency is lesser than phase crossover frequency which we have obtained here, the system is said to be a stable system.